You are welcome to Senior 2 Chemistry. My name is Mbumza Tyson, and those of you who already know me. Today we are going to look at a topic which we are calling acids, bases, and salts. Acids, bases, and salts. So this is a topic on Senior 2 syllabus that we are going to handle. So we are going to begin with acids. So someone can ask you, what is an acid? Because we have many people in our society who like to use the word acid. They pour the acid on me, And then there's also an anonymous assumption, which is actually true, that we have some acid in our body. In fact, that acid is called hydrochloric acid. You see that? So basically, we're saying that at our level of Senior 2, we have already encountered with acids, right? So what would be the definition of an acid? We're going to say an acid is a substance which, when it dissolves in water, it produces hydrogen ions as the only positively charged ions. We're saying an acid is a substance. An acid is a substance which when dissolved in water, produces hydrogen ions. As the only positively charged ions. It is important to note that an acid is, in fact, some books call it a proton donor. It produces hydrogen ions in solution as the only positively charged ions. A clear example, that hydrochloric acid which we like, hydrochloric acid. In fact, its formula is HCl. When it dissolves in water, I can say HCl, when it dissolves in water, it produces what we call H plus from hydrogen ions. Hydrogen becomes H plus, it is become H plus aqueous, then plus the chloride. But the chloride is going to be a negative. Remember that the charge depends on the valency of the element. Hydrogen, valence 1, so plus. Chloride, valence 1, still also minus aqueous. So you realize that the only positively charged ions produced by hydrochloric acid is actually hydrogen ions. So any substance which produces hydrogen ions as the only positively charged ions is called an acid. It's called the what? An acid. So basically that is it. So we are going to look at types of acids. They are what we call mineral acids. Like the word sounds, mineral acid. This comes from minerals. They are common laboratory acids, most of them. An example we have sulfuric acid. Its formula of sulfuric acid is H2SO4. Sulfuric acid is H2SO4. Then we also have an acid which is similar to sulfuric acid but called sulfurous acid. It's also amino acid which is actually H2SO3. Then the hydrochloric acid which we have already talked about also belongs here. Hydrochloric acid. Its formula is HCl. Then we have what we call nitric acid. Its formula is NO3. Someone might ask a question. Why is there a 2 here, and no 2 here? Well, remember when we are writing the formula of compounds, valence is very important. We have already said that valence is the mother of chemistry. Valence is the mother of chemistry. That means that in this case, if I want to write the formula of sulfuric acid, I just need to know that sulfuric acid comes from 2 radicals, a hydrogen ion and a sulfate ion. But the sulfate has valence 2, hydrogen has valence 1. So when they swap the valence, the 2 for the sulfate comes here. The same applies with the sulfite. SO3 sulfite has valence 2, so it comes here. Whereas here for hydrochloric acid, the Cl has valence 1. Even for nitric acid, the NO3 has valence 1. The NO3 also has valence 1. So you see that? Then we also have another acid which looks like a nitric acid, but this one is called nitrous. Nitrous acid is NO2 HNO2. That is nitrous, nitrous acid. We have another acid which we can call phosphoric acid. Phosphoric acid. We have another acid called phosphoric acid, which is actually H3PO4. In this case, for it has a 3 because the valence of the phosphate is a 3. The valence of the phosphate is a 3. Those are some of the examples of acids that we always use, especially in the lab. We have sulfuric acid, sulfurous acid, hydrochloric acid, we have nitric acid, nitrous acid, phosphoric acid. We even have another acid called phosphorus acid. Phosphorus acid is H3PO3 instead of PO4. Phosphorus acid. Phosphorus. It is also amino acid, H3PO3. There is another that I had forgotten and very common called the carbonic acid. Carbonic acid, for it is H2CO3. H2CO3. But one thing is common for all these acids, as we have already seen. There is hydrogen everywhere. There is hydrogen everywhere. Why? Because by definition, an acid is a substance which, when dissolved in water, produces a hydrogen ion as the only positively charged ion. So, for any compound called an acid, you realize that apart from their radicals which are positive, which are negative, the only other ions that are in solution that are positive are hydrogen ions everywhere. I think you can see hydrogen ions. Then we also have what we call organic acids. The first type we called it mineral acids. But now we want to look at organic acids. When you look at organic acids, these are acids that are derived or that come out of organic substances. When we continue with chemistry, we shall talk about what we call organic substances. Organic substances, these are substances which are derived from compounds of carbon. The major component in the skeleton of an organic compound is carbon and hydrogen. Do you see that? So, organic compounds can give us what we call organic acids. And we're saying organic acids. I have examples. The first example we can talk about ethanoic acids. In fact, most of these acids, we call them carboxylic acids. Carboxylic acids. Organic acids are actually also known as carboxylic acids. And we have said a clear example is ethanoic acid. You will allow me to give you the name. I mean the chemical formula. The chemical formula is CH3COOH. CH3COOH. Do you see that? That is ethanoic acid. We also have what we call methanoic acids. Methanoic acids. We also have what we call methanoic acid. Methanoic acid, its formula is HCOO. HCOOH. That is methanoic acid for you. Do you see that? Someone might ask, now this one, how come this one has the H at the end, but it also has some H here, then this one has the H here and the H here. You don't have to worry about this formula. I'm going to show you how they ionize later on. I'm going to show you how they ionize later on. But for now, what you need to pay attention to is their formula. Just look at their formula, try to understand it. If you can't understand it, then postpone it to a later moment when I'll be explaining it to you. So these are the different classifications of acids. Acids can either be mineral acids, but they can also be organic acids. There's also another classification of acids, which depends on the strength of the acid. Which depends on the strength of the what? Of the acids. Like we can say, some acids are strong, other acids are weak. Some are strong, others are weak. And the strength of the acid, we shall say, is the ease with which acids can ionize. Is the ease with which acids can what? Can ionize. So let's look at the strength of the acids. Let's look at the strength of the acids. Strength of the acids. So to talk about the strength of the acids, we are majorly interested in how easy can an acid ionize a solution. Remember, by definition, we have said an acid is a substance which, when dissolved in water, produces hydrogen ions as the only positively charged ions. So from the definition, we are going to say that an acid must ionize to give hydrogen ions. But there are some which ionize easily, but there are some which find it hard to ionize. Do you see that? For example, we are going to say, let's first define the strength of the acid. We are saying this is the ease, is the measure of the ease. With which an acid ionizes in solution, to form or to give hydrogen ions. Is with which an acid ionizes in solution to give hydrogen ions. Do you see that? So, we are going to categorize an acid into two classes according to the strength. We are beginning with the strong acids. Of course, if one acid is strong, then the opposite of strong is going to be weak. So one acid can be strong, then the other can be weak. So if we are talking about strong acids, so let's look at the definition. We are saying these are acids. These are acids which completely ionize in solution. They completely ionize in solution to form many hydrogen ions. Or to form a high concentration of hydrogen ions. You see that? To form a high concentration. To give a high concentration of what? Of hydrogen ions. they completely ionize in solution. And most of the amino acids are actually strong, apart from a few. So the examples I'm giving there, examples. So my first example is the common one, which I have already talked about, hydrochloric acid. Hydrochloric acid. Hydrochloric acid. Hydrochloric acid, you have said, is HCl. You have said this one is completely ionized in solution. So it means if it was HCl aqueous in solution, it is going to completely ionize. If there is complete ionization, then we are going to use an arrow, a full arrow. Then it shall give us hydrogen ions, aqueous, and then chloride ions, also aqueous. Why am I saying aqueous for both? Because the compound is aqueous. A compound cannot ionize unless it is aqueous. Ionization, like the word ionization, means formation of ions. So hydrochloric acid forms ions. The hydrogen is a positive. That means the chloride is negative. But you have to remember the what? The valence. Is that okay? Next we have dilute sulfuric acid. Why am I putting the word dilute? Because if it is concentrated, then it will be weak. It must be dilute. It must be dilute. So the formula of sulfuric acid, we say, is H2SO4. And this is still aqueous because it is dilute. It completely ionizes to give, of course, hydrogen ions, and then SO4, which we call sulfate. Hydrogen ions, they are hydrogen ions, aqueous, but I think you can see that there are two of them. There are two of them. So you put a 2 here. Then plus the sulfate ions, SO4, sulfate. But the radical of the sulfate has a valence of 2. Has a valence of 2. So we just put 2 what? 2 minus. Because its valence is 2. Do you see that? This is the ionization of sulfuric acid. Another example of strong acid, we have nitric acid. We have nitric acid. Nitric acid is HNO3. This is the formula of nitric acid. If we want to look at the ionization, it will be HNO3 aqueous. This one completely ionizes. When it completely ionizes, it is going to give us the hydrogen ion, of course, H. So it's going to be H plus aqueous. Then plus the nitrate. The nitrate has valence 3. So it shall be NO3. I mean it has valence 1. NO3 aqueous. So this is the ionization of the acid in that sense. But you see that all of them, they are giving hydrogen ions as the only positively charged ion. Do you see that? So basically, these are a few of the examples of strong acids. These are the few examples of the strong acids. Let us look at weak acids. Let us look at weak acids. These are they are going to say these are acids. These are acids which partially ionize. These are acids which partially ionize in solution. To produce few hydrogen ions. produce few hydrogen ions in solution. Okay, it's already there in solution. So the other thing we can say is that most of the substance of the acid, most of the acid remains in its molecular state. Most of the acid remains in its molecular state. They partially ionize. Partially means part of it ionizes, another part does not ionize. Part ionizes, another remains without being ionized. I've said the bigger part remains in its molecular state. It means the ionization is just a smaller percentage. The ionization is just a smaller percentage. And in our examples, we say, in fact, we're going to say most of the organic acids are weak electrolyte. Weak acids. A clear example is ethanoic acid, C83 ethanoic acid. So this is our first example, ethanoic acid. Ethanoic acid, remember the formula? It was C83 COOH. I know most senior 2 students they don't like the formula because it is complicated for them. But just look at it in this way. It is an organic compound which we shall study later. However, its ionization in that case is going to be partial. We have said it is partial ionization, and if we are trying to relate partial ionization, we use double arrows. When you see a double arrow, you know we are talking about partial ionization. So this first part, up to hydrogen, it is going to split. So the compound is going to split into this first part up to hydrogen and then hydrogen. Is that okay? So it's going to be C83 COO minus aqueous, and then plus H plus, also aqueous. This is quite different from the amino acid, because the amino acid, when you write the amino acid, you begin with hydrogen. Hydrogen chloride, hydrogen sulfate, hydrogen nitrate. But for organic acids, you first write the radical in the beginning, and then hydrogen later. So when it ionizes, it gives you this and that. But it is partial ionization. Then another organic compound, organic acid, we call it methanoic acid. This is ethanoic C83 COOH. So this is methanoic acid, which is actually C83 CH3 methanoic acid. It is actually HCOOH. So that's what we have. So if it was to ionize, it is aqueous. Aqueous means it is dissolved in water. AQ. Aqueous. Aqua means water, right? If we use double arrows to mean partial ionization, so this one is going to ionize independently and that one independently, leading to the formation of HCOO minus and then H plus. HCOO minus aqueous and then also H plus and also H plus. This is a weak acid, that is a weak acid. Then we also have amino acids, which are also considered to be weak. We have an example of carbonic carbonic acid. Carbonic acid is considered to be weak, and because of its weakness, that's why sometimes when we use rainwater, the acid that has dissolved in rainwater does not kill. It doesn't kill. It does not affect our bodies because it is slightly acidic. Why do we say so? Because we know that when water is falling from the atmosphere contains some carbon dioxide, right? And that carbon dioxide reacts with water, that is rain falling from down, leads to the formation of carbonic acid, which is actually H2CO3. H2CO3. Do you see that? So the water that falls from the sky is not pure, as many people want to call it. Why? Because the carbon dioxide present in the atmosphere tends to dissolve in the rainwater, leading to the formation of a weak acid called carbonic acid, but it's not dangerous since it is weak. And we want to look at how it ionizes, partially. I want to look at its partial ionization. So we have H2CO3 aqueous, partially ionizing, leading to the formation of, we are going to have hydrogen ions, just one of them, aqueous, and then the other one will remain, leading to the formation of hydrogen carbonate. Partial ionization. One of the hydrogens has ionized, then the other has not. It has remained with the carbon, leading to the formation of a radical called hydrogen carbonate. Do you see that? But then sometimes we can also react it as aqueous, leading to the formation of two hydrogen ions, aqueous, and then the carbonate, two minus. If it is hydrogen carbonate, its radical hydrogen carbonate has valence 1. The carbonate has valence 2. But for both cases, it is partial ionization. That's why we use the double arrows. That's why we have said that for most of these compounds, the biggest part remains in the molecular form. The biggest part remains, even here, the biggest part remains in the molecular form. The part which is ionized is a very small percentage of the substance. The part which is ionized is a very small percentage of the substance. Another example of a weak acid, we can look at sulfurous acid, we can look at phosphorus acid. Most of those acids are weak. We can look at nitrous acid and their ionization. For example, if you look at nitrous acid, that is NH2O, nitrous acid, HNO2, nitrous acid, it partially ionizes, this is aqueous, leading to the formation of few hydrogen ions, and the nitrite is like that, NO2 minus nitrite. Sulfurous acid, some people call it sulfuric acid, sulfurous acid. This one we say is H2SO3, that is H2SO3, that is H2SO3 aqueous, partially ionizes. Partial ionization leading to the formation of two hydrogen ions because there are two, and then the sulfate, and then the sulfite, aqueous, and then the sulfite. Remember the other thing we said, when you look at sulfuric acid, we said it is a stronger acid when it is dilute, Meaning when it is concentrated, it is a weak acid. Let me show you how concentrated sulfuric acid ionizes. If I'm going to wrap this and replace it with corn sulfuric acid. Concentrated sulfuric acid. Concentrated sulfuric acid. That is H2SO4. In fact, we shall say when this acid is cold, then it is in liquid form. It partially ionizes. When it was dilute, remember, when it was dilute, it was aqueous. Do you see that? But now, since it is concentrated, then we say liquid. Do you see that? That means that in this case, it has a small amount of water and the bigger percentage of it is in a molecular form. That's why we say liquid. It partially ionizes, giving you one hydrogen ion plus the other hydrogen, because there are two. The other hydrogen will remain forming hydrogen sulfate, which is HSO4 minus aqueous. Just like how we form the hydrogen carbonate here, even here we are forming hydrogen sulfate. I hope you can appreciate that. We're forming hydrogen sulfate, and hydrogen sulfate as a radical has valence 1. It has valence 1. So basically, that is it about the strength of the acids. Now let's look at the basicity of an acid. Let's look at the basicity of an acid. Basicity of an acid. Basicity of an acid. This is what we call basicity of an acid. So when you talk about basicity of an acid, you're looking at the number of hydrogen ions that are released by 1 mole of an acid in a solution. The number of, this is the number of hydrogen ions. Number of hydrogen ions that are released. In fact, we can call it the number of moles. The number of moles of hydrogen ions that are released by 1 mole. 1 mole of an acid. 1 mole of an acid. Number of moles of hydrogen ions that are released by 1 mole of an acid. There is something that you have noted as we were discussing about acids. There was something you had to note. Some acids have 2 hydrogen ions, some have 3, some have 1. Is that okay? So that determines the basicity of an acid. So we are going to say some acids release. In fact, by definition, released by 1 mole of an acid, I was supposed to say in solution. Some acids release 1 mole of hydrogen ions, another can release 2, another can release 3. This will determine the class. So the first group are called monomeric acids. Monomeric acids. Like the word mono means 1. Mono means 1. It means these ones, they release. These release 1 mole of hydrogen ions. Hydrogen ions. These ones release 1 mole of the acid releases 1 mole of hydrogen ions. And a clear example, e.g., we have HCl, HNO3. These are the clear examples of monobasic acids. It's just one hydrogen ion. Just one hydrogen ion. And the ionization here we have already shown you, but I can show you again. For HCl, that is hydrochloric acid, it will ionize, giving us H plus appears, and then also Cl also appears. Do you appreciate that? One mole of an acid, there is a silent one here, releases 1 mole of hydrogen ions. So we call it monobasic. 1 mole of acid, 1 mole of the acid releases 1 mole of hydrogen ions in solution. 1 HCl releases 1 hydrogen. Do you see that? 1 NO3, HNO3 aqueous releases 1 hydrogen, and then the nitrogen. Monobasic. What about dibasic? Dibasic acids. What about dibasic acids? In this case, 1 mole of the acids releases 1, in fact 2, in that case because of that, 2 moles of hydrogen ions in solution. And a clear example, we have sulfuric acid. Sulfuric acid, when it is light, aqueous. This one ionizes to give 2 hydrogen ions plus the sulfates. Do you see that? 2 hydrogen ions are released by 1 of the acid. There is a silent one here. 1 acid releases 2 hydrogen ions there. That is dibasic. That is dibasic. Look at carbonic acid. H3CO3 aqueous. H2 I mean. This one gives 2 hydrogen ions and the carbonate. 2 hydrogen ions and the carbonate. 1 acid here has released the 2 hydrogen ions. So you can easily tell the basis of an acid by looking at the formula of the acids. When you see a 2 here, you know that is dibasic. You see a 2 here, you know that is dibasic. Here, it's just 1. Then there are also these ones which are called tribasic. Tribasic acids. In this case, 1 mole of an acid, 1 mole of an acid releases how many? Releases 3 moles. Releases 3 moles of an acid, of hydrogen ions. Releases 3 moles of hydrogen ions. 1 mole of an acid releases 3 moles of hydrogen ions. A clear example there is phosphoric acid, e.g. phosphoric acid. Do you remember the formula of phosphoric acid? Phosphoric acid, that was H3PO4. H3PO4. You already see this. You already see the 3 there. So this is already an indicator that it is a what? Tribasic. Tri means 3. So its ionization H3PO4 aqueous is going to form 3 hydrogen ions, and then the phosphate has valence of 3. So that's why we put 3 minus there. 1 silent here produces 3 hydrogen ions. That's why we say it is tribasic. That's why we say tribasic. So this is the classification of acids. We have classified acids as either amino acids or organic acids. We have classified acids as either weak acids or strong acids. We have also classified acids based on their basicity, saying that some are monobasic, others are dibasic, and others are tribasic. All the acids that there is out there can be classified into these 3 categories, looking at either it is mineral acid or organic, or either it is strong or it is weak, or in terms of their basicity, the number of moles of hydrogen ions that an acid, 1 mole of an acid, releases in solution. Is that okay? Now, let us look at some of the physical properties of an acid. Let us look at some of the physical properties of an acid. Okay. Properties of acids. Properties of acids. So like the word acid comes from the word acidus. And the word acidus means sour. So the first property, the first physical properties. The first one, we shall say, they have a sour taste. They have a sour taste. The word acid comes from the word acidus, which means they have a sour taste. They are sour. Of course, you know the difference between sour and bitter. Bitter is different from sour. So you can try to find out sour. A sour taste is like the taste of chili, kamla. It is sour, it has that burning sensation on the tongue. So they have a sour taste. Then secondly, they are corrosive. They are corrosive. By meaning they are corrosive, they have a burning sensation on the skin. They can burn your skin. That's why the acids are extremely dangerous. If you are a student of Senior 2, don't come close to an acid unless there is a teacher around you to either guide you how to handle the acid or to dilute it for you. I think you have seen many people who have, burnt other people's faces, especially women who are fighting for men. They burn each other with acid and thereby deforming someone's skin, someone's face for good. So they are corrosive, they are also poisonous. Don't come close to them. Then the next one we are going to say, they change litmus paper. They change litmus paper red. So if you are testing with the litmus paper or you're testing with litmus solution, it changes red. They also have an effect on other indicators, because we have many other indicators. We have phenolphthalein indicator, we have methyl orange indicator, we have methyl blue, we have methyl red, we have universal indicators. All these indicators are there to measure the acidity or the alkalinity of a substance. And acids have a direct impact on indicators. So these are some of the physical properties. Let's look at the chemical properties of acids. Chemical properties of acids. So what we are going to say is acids react with metals, react with Carbonates react with hydrogen carbonates. Then they also react with bases. The first one, reaction with metals. Acids react with metals to liberate hydrogen gas, leading to the formation of their own salts. Acids react with metals. Liberating hydrogen gas. With the formation of the metal salts of the corresponding metal salts. E.g., if the metal we are dealing with is sodium, so I am having sodium. Sodium is Na plus. If the acid we are dealing with is sulfuric acid, so sulfuric acid is H2SO4 aqueous. So what we are going to form, remember when we were studying about types of reactions, we said these kinds of reactions are displacement reactions, whereby in this case sodium will displace hydrogen. So we shall form sodium sulfate. Someone is going to ask me, teacher, why have you put a 2 here? Remember we said when we are forming compounds, you come here, maybe this is my sodium, that is my sulfate. We need to know their valences. The valence of sulfate is 2, the valence of sodium is 1. This one comes here, this one comes there. So we end up with Na2SO4. So this 2 here represents the valency of the sulfate, showing that actually the sodium has valence 1, then plus, of course this hydrogen has been displaced. But remember, hydrogen is diatomic, and it is displaced in the form of a gas. So that's what we are saying, that the acids react with the metals to liberate hydrogen gas with the formation of their metal salts. Now in this case, this is sodium sulfate, which is a salt. We have a part of this topic called salts that we are going to discuss in details so that we can understand. Then another one, we can use sodium, we can use magnesium. Let me use magnesium as a metal, plus an acid. I can use hydrochloric acid. However, let's go back to this equation. We did not balance the equation. In chemistry, we always say if our equation is not balanced, then it is not correct. If an equation is not balanced, it's not correct. Therefore, this is not a correct equation. We have to balance it. So in this case, we have 1 sodium. Here, the sodium atoms are 2. So to make them 2, I have to multiply a 2 here. 2 sodium. Hydrogen here, they are 2. So that one balances. The sulfate is 1 here, but the sulfate is 1 there. So that one balances. Looking at this, magnesium and hydrochloric acid. So we form, we have magnesium and we have the chloride. Remember, these are displacement reactions, whereby the first one goes with the last. That's how we always do it. And then we say we form magnesium chloride. It would have been like this, but magnesium has valence 2 chloride has valence 1. So the chloride, the valence 2 for magnesium comes this side. So it becomes MgCl2, and we call this one aqueous. We call that one aqueous. The reason why we are calling them aqueous is because these metals are dissolving in the acid. So because they are dissolving in the acid, they form a solution. And a solution in chemistry is represented by AQ. AQ means a substance dissolved in water. Substance dissolved in water. So the magnesium has gone with the chloride, hydrogen has remained. So because hydrogen has remained, what will happen? We are going to liberate it off as hydrogen gas. But I have said hydrogen gas is diatomic, so it is H2. It is diatomic. The equation balances? No, it doesn't balance. So what do? We try to balance it. Magnesium 1, magnesium 1. Hydrogen, 1 hydrogen atom. Here hydrogen, there are 2. So to balance, I have to put a 2 here. Don't attempt to put a 2 in the middle of the compound or at the end of the compound, because you would have changed its formula. You would have changed its chemical formula. So what you have to do is you make sure you write it in front of the compound so that it does not change the molecular formula, the chemical formula of the compound. The last one that I want to give for today is I can use Z and an acid called nitric acid. Zinc and nitric acid. This is a metal, this is an acid. So zinc will react with the nitrate. Nitrate, remember, has valence 1, zinc has valence 2. So we are going to form zinc, nitrate. Then we swap the valences. Zinc has valence 2, so it has to come here. But I cannot say NO6. No, I have to put brackets and I bring the 2 there. Nitrate has valence 1, so even if I don't show the 1 there, right? Aqueous, then plus hydrogen. Hydrogen. This hydrogen has to be this place. And to balance, zinc balances hydrogen. This is 2. 1, this is 2. So to balance, I have to put a 2 here. But this 2 multiplies on the nitrate, but the nitrate is already 2 already there. So even this one balances, just like this one was balancing. This 2 was for hydrogen, but it was also for the chloride, which was already 2 there. So that is the first chemical property of acids. And the next time we are discussing, we shall be looking at other chemical properties of acids. For now, shalom.